Hi! In this video we will cover categorical and ordinal features. We will overview methods to work with them, in particular, what kind of pre-processing will be useful for each model type. What is the difference between categorical and ordinal features? And how we can generate new features from them. First, let's look at several rows from the Titanic dataset and find categorical features here. Their names are sex, cabin, and embarked. These are usual categorical features, but there is one more special, the P-class feature. P-class stands for ticket class and has three unique values, 1, 2, and 3. It is ordinal, or, in other words, ordered categorical feature. This basically means that it is ordered in some meaningful way. For example, if the first class was more expensive than the second, all the more the first should be more expensive than the third. We should make an important note here about difference between ordinal and numeric features. If P-class would have been a numeric feature, we could say that the difference between first and the second class is equal to the difference between second and the third class. But because P-class is ordinal, we don't know which difference is bigger. As with numeric features, we can't sort unique values of ordinal feature the other way and expect to get similar performance. Another example of ordinal feature is a driver's license type. It's either A, B, C, or D. Or another example, level of education: kindergarten, school, undergraduate, bachelor, master, and doctoral. These categories are sorted in increasingly complex order, which can prove to be useful. The simplest way to encode a categorical feature is to map its unique values to different numbers. Usually, people refer to this procedure as label encoding. This method works fine with trees, because tree methods can split feature and extract most of the useful values in categories on its own. Non-tree-based models, on the other side, usually can't use this feature effectively, and if you want to train linear model, KNN, or neural network, you need to treat a categorical feature differently. To illustrate this, let's remember an example we had in the beginning of this topic. What if P-class of 1 usually leads to target of 1, P-class of 2 leads to 0, and P-class of 3 leads to 1? This dependence is not linear, and linear model will be confused. And indeed, here we can plot linear model's predictions, and see that they all are around 0.5. This looks kind of sad. But trees, on the other side, will just make two splits, selecting each unique value and treating it independently. Thus, decision trees could achieve much better score here, using this feature. Let's take another categorical feature and again apply label encoding. Let this be the feature embarked. Although we didn't have to encode the previous feature P-class before using it in the model, here we definitely need to do this with embarked. It can be achieved in several ways. First, we can apply encoding in the alphabetical or sorted order. Unique values of this feature, namely S, C, Q, thus can be encoded as 2, 1, 3. This is how label encoder from Skylern works by default. The second way is also label encoding, but slightly different. Here we encode a categorical feature by order of appearance. For example, S will change to 1 because it was met first in the data. Second is C, and we will change C to 2, and the last is Q, which will be changed to 3. This can make sense if rows were sorted in some meaningful way. This is the default behavior of pandas factorize function. The third method I will tell you about is called frequency encoding. We can encode this feature via mapping values to their frequencies. If in 30% of rows embarked is equal to C, in 50 to S, and the rest 20 is equal to Q, we can change these values accordingly: C to 0.3, S to 0.5, and Q to 0.2. This will preserve some information about values distribution and can help both linear and tree models. First ones can find this feature useful if value frequency is correlated with target value, while the second ones can have less number of splits because of the same reason. There is another important moment about frequency encoding. If we have multiple categories with the same frequency, they won't be distinguishable in this new feature. We might apply a rank operation here in order to deal with such ties. It is possible to do like this. There are other ways to do label encoding, and I definitely encourage you to be creative in constructing them. Okay, we just discussed label encoding, frequency encoding, and why this works fine for tree-based methods. But we also have seen that linear models can struggle with label-encoded features. The way to adapt categorical features to non-tree-based models is also quite straightforward. We need to make new column for each unique value in the feature and put one in appropriate place. Everything else will be zeros. This method is called one-hot encoding. Let's see how it works on this quick example. So here, for each unique value of p-class feature, we just created a new column. As I said, this works well for linear methods, KNN or neural networks. Furthermore, one-hot encoded feature is already scaled because minimum of this feature is 0 and maximum is 1. Note that if you have a few important numeric features and hundreds of binary features produced by one-hot encoding, it could become difficult for tree methods to use first ones efficiently. More precisely, tree methods will slow down, not always improving their results. Also, it's easy to imply that if categorical feature has too many unique values, we will add too many new columns with few non-zero values. To store this new array efficiently, we must know about sparse matrices. In the nutshell, instead of allocating space in RAM for every element of an array, we can store only non-zero elements, and thus save a lot of memory. Going with sparse matrices makes sense if number of non-zero values is far less than a half of all values. Sparse matrices are often useful when we work with categorical features or text data. Most of the popular libraries can work with these sparse matrices directly, namely XGBoost, LightGBM, Sklearn, and others. After figuring out how to pre-process categorical features for tree-based and non-tree-based models, we can take a quick look at feature generation. One of most useful examples of feature generation is feature interaction between several categorical features. This is usually useful for non-tree-based models, namely linear model and KNN. For example, let's hypothesize that target depends on both p-class feature and sex feature. If this is true, linear model could adjust its predictions for every possible combination of these two features and get a better result. How can we make this happen? Let's add this interaction by simply concatenating strings from both columns and one-hot encoding it. Now linear model can find optimal coefficient for every interaction and improve. Simple and effective. More on feature interactions will come in following weeks, especially in advanced features topic. Now let's summarize this video. First, ordinal is a special case of categorical feature, but with values sorted in some meaningful order. Second, label encoding basically replaces unique values of categorical features with numbers. Third, frequency encoding, in its turn, maps unique values to their frequencies. Fourth, label encoding and frequency encoding are often used for tree-based methods. Fifth, one-hot encoding is often used for non-tree-based methods. And finally, applying one-hot encoding to combinations of categorical features allows non-tree-based models to take into consideration interactions between features and improve. Fine, we just sorted out feature pre-processing for categorical features. and took a quick look on feature generation. Now you will be able to apply these concepts in your next competition and get better results.